Hi again. So the derivative doesn't have to exist everywhere. Properly speaking, the derivative doesn't have to exist anywhere. It's possible to create continuous functions that don't have derivatives at any point. Those tend to have very convoluted, very artificial definitions. But we can have a perfectly normal, perfectly nice, perfectly well-behaved function that does not have a derivative at every point. So let's just run through why that would occur. So in terms of for this question to be interesting at all, the function itself has to be defined at the point, right? If the function isn't defined at a point, of course there's no rate of change at the point. So the question we're really asking is, how can f of c be defined, but f prime of c not be defined? And there are three classic ways that this could happen. So we'll just run through those three. If this function is not continuous at C, f prime of C will not exist. And most of our day-to-day functions are continuous where they're defined. A So you don't need to memorize this name, but a kind of famous example of a function with a discontinuity is the Heaviside function. It's defined piecewise. It's zero when x is negative. It's 1/2 at zero, and it's 1 when x is positive. Heaviside was an engineer. This is a function that shows up in electrical engineering. It represents a switch being flipped. The switch is off, it's flipped, then it's on. So this function is defined at zero. H of 0 equals 1/2, but it's not continuous at 0. H prime of 0 does not exist. So that's the first way that a function might be defined at a point, but not have a derivative at that point. The second way, and I'll state this not very formally, but if x equals c is a sharp corner, then the derivative does not exist. And the sort of canonical example of this, the example you always see, is f of x equals the absolute value of x. So the graph of the absolute value is two straight line segments that intersect at a 90-degree angle. So you see what I mean about a sharp corner here on the Cartesian plane. This is happening at the origin. It's happening at x equals 0. Well, the absolute value of 0 is 0. No problem there. The derivative at 0 does not exist. And maybe it's easiest to think of this in terms of tangent lines. The derivative gives the slope of the tangent line. The derivative gives the direction of the curve. Well, what's the direction at the origin? If they're going down and to the left, that is, if they're approaching the origin from the left-hand side, the direction is down and to the left. If they're approaching the origin from the right-hand side, the direction of the curve is down and to the right. So you see the slope of this line down and to the left, sorry. You see the slope of this line down and to the left, and the slope of this line down and to the right. These are different. So the derivative doesn't exist. And that's as opposed to a curve without a sharp corner. If you approach this curve I just drew from the left-hand side, you go in this direction. If you approach it from the right-hand side, you go in this direction. You see we've gotten a straight line, and that straight line has a slope, and that slope is the derivative. It's fundamentally different from this, where we got two straight lines with two different slopes. And then the third classic way the derivative could fail to exist at a point. The derivative's the slope of a tangent line. So there is one class of lines that do not have slopes, and those are vertical lines. If the tangent line is vertical at x equals c, the derivative will not exist. And the classic, well, there are a few kind of examples we could call classic, but maybe the square root function is the most classic. The square root function, we're probably familiar with its shape. It starts at the origin, and then it goes up as we move to the left, as we move to the right, making that mistake a lot this video. And the tangent line at the origin turns out to be the y-axis. So f prime of 0 does not exist. And this one you can just see. If we use the power rule, we've done this example in another video. It's 1 over, the derivative is 1 over 2 times the square root of x. And we can just look at this formula and see that if we try to plug 0 into it, we get a division by 0 error. And I guess the only thing I have to say, I did 3 examples. In all of them, the derivative doesn't exist at 0. I mean that's kind of a coincidence. Like I could take this absolute value example, and I could define g of x to be the absolute value of x minus 2. And now the sharp corner exists at 2. So g prime of 2 does not exist. So in these 3 kind of canonical examples, the derivative doesn't exist at the origin specifically, but that's a coincidence. We can very easily create examples where the derivative fails to exist at another value.